I just want to start off with the calculation I did last time and then finish off. So we were discussing so let me recall. We were discussing conditional density and last class. So we had two continuous random variables x and y, for which we had a joint density. And then from that, we try to infer how does one compute the chance of x equal to a distribution of x given the value of y, given particular value of y. So let me just start off with that. So I had said that x and y are two continuous random variables. And having joint density f. You let the marginal of f be let's say f sub y be the marginal of density of y. And f's then the conditional density. So let's say you take a b in R, for which f sub y at the point b was positive. The density gave a positive number. And you assume that f is continuous at b. Then what I said last time was the conditional density of x given y equal to b is, so the idea was that you look at f of x given the point y equal to b at a point x is just you evaluate the joint density at x comma b and the whole thing divided by f sub y. And we had covered a derivation of this last time. So then the same flips over if you have the reverse. If you have, let's say, f sub x be the marginal density of x, and let's say you have a and r, for which f sub y of a is positive. And f is continuous at a, f of x of a is positive, and f is continuous at a. Then again the conditional density of y given x equal to a is given by, you reverse the thing, you have f y given x equal to a at a point y, you evaluate joint density at the point a comma y, the whole thing divided by f sub x at the point. These are two key sort of ideas that we discussed last time. We make it a bit smaller so you can see the whole thing on one page. This is what we were discussing. The density of, you have a joint density that describes the dependency of the two random variables, and then you have a marginal density of f and given of y and a marginal density of x given as f sub x. Then you can think of the conditional density of x given y equal to b as this as a joint density divided by the the marginal density. Let me do a quick example and so understand this whole yeah. So, example, let's say I call it 5.4.12 in the book. You let x and y have joint density. Let's say joint PDF. Let's say call it f, given by let me call it as f of x comma y. Let me write a double exponential, so like root 3 by 4 pi e to the minus 1/2 x squared minus xy plus y squared. This is for both x and y now. X and y in R. That's how the density looks like. Okay, the joint. Now, let me try and see from this example, let me try and see if I can compute the marginal of x first. Okay, so first is that joint. Let's do the marginal of x. So how do you do that? So we know that f sub x at the point x is going to be the integral from minus infinity of f sub x at the point y dy. Right? You integrate out y, you get the density of x. Now what is this? This is just like we go about. It's just this formula, right? So you just copy the formula down. Duplicate it, you bring it down. So it's going to be just this integral dy. So it's going to be this minus infinity to infinity of this thing dy. So now here these are all constants. So let me just rewrite this in different colors so it's clear what the integrand is. So just the root 3 by 4 pi comes out. This comes as a constant. And let me write the integral in red, which is minus infinity. Then this x is constant, so I have e to the minus x squared by 2 that comes out by itself, no problem. And what's left is e to the minus x, and then I have everything else depends on y. So xy plus y squared dy. That's the integral. So now all you observe is that you have to just complete the square and divide by 2. This is minus of xy. The end of the thing is minus of xy plus, let me put a bracket here, xy plus y squared by 2. That's what I have as a computation. So I have to evaluate. So the trick here is that you observe that this guy is just the same as, so you observe, the first trick is to observe that y squared plus xy is the same as y minus x by 2 the whole squared. And then all I do is I have to add another, since I'm adding an x squared by 4, I have to subtract an x squared by 4. This is what happens, right? If I add a thing, I have to subtract. Now let's observe this. So that means here x is a constant. So let me write this again in red for you, so it's clear. So let me write the y is in red. So I have to go back here and say y squared plus x times y is this. That's it. So therefore, what happens now? Therefore, if you want to evaluate the integral, go back here. So this is equal to, the integral is equal to root 3 by 4 pi e to the minus x squared by 2. Then this inside, I replace it by this, so I get minus x squared by 8, or plus x squared, minus x squared by 8. Make a mistake, no, plus x squared by 8, I get this. then the integrand is minus infinity e to the minus, then I have minus 1/2 of y minus x squared x by 2 whole squared dy. So dy is better. So that's exactly what I have, right? So it's like the integral looks exactly like this. So now you observe a little bit. So what happens now? This looks like, so what you do is, my claim is that this integral right here looks familiar, right? Because this is like a density of a normal random variable with mean x by 2. So this is an exercise to observe that from facts about normal density, normal PDF, that the integral from minus infinity to infinity e to the minus 1/2 of y, I can leave that in black again, minus this whole squared dy, this whole squared dy, sorry, this is blue, dy is in fact square root of 2 pi. That's something you have to evaluate. Because 1 over 2 pi of this guy is going to be integrated to 1, so it's different. Therefore, the above is equal to now, I have root 3 by 4 pi, right? I have e to the minus x squared by 2 plus x squared by 8. I'll write that as a minus 3x squared by 8, right? That's what it is. And then I have this integral is root 2 pi. That's all I have. That's root 2 pi. Once I have this whole thing, so for what I have f sub x at the point x, is what I have everywhere here. Go back up, f sub x at x is going to be equal to, so I have e to the minus 3x squared by 8, and I have a root 2 pi here and a 4 pi here. Okay. So a root 2 pi and a 4 pi would just give me a, I would think of this as root 2 pi at the bottom, and I have a root 3, and I have a root 3 pi. So it's equal to, I have 1, and I have a root 3 pi. Alright. So this is for any epsilon. So if you observe a little bit, then what's happening now? This just looks like that means, if you think a little bit, what is x distributed as? It looks like a normal random variable, right? And the mean is 0, and the variance is 4 by 3. That's what exact normal is. This from facts about normal density is exactly right. So that's a simple calculation one can do. Right? So one can easily do, if x is given by John density like this, then the marginal is given by a normal with mean 0 and variance 4 by 3. That's simple calculation one can do. Now, one thing you observe is that, let me just go a double screen. So if you just observe a little bit in this example, see the density function is symmetric about x and y, right? F of xy is same as f of yx. So this calculation, if I just replace the entire x's by y's and y's by x, I'll get the same fact for y. So it's a simple fact. I'll just let you think a little bit. It's a simple exercise to think about. That so you observe. So first thing you observe two things. You observe that f of x comma y is same as f of y comma x for all x and y in R. Right? So this would imply that f sub y given x equal to x at the point, sorry, density. I'm copying the here. F sub y at the point y would be the same as the calculation for x. Would also be equal to root 3 by root 4 e to the minus 3y squared e to the minus 3y squared by 8 over root 2 for y. So that means the y also is normal with mean 0 and variance 2 by. And that is because I can repeat the above calculation completely for y as I did for x. Oh, so now I have two facts now. I have y is this, x is this, and the joint density. So let's try and do some simple calculation. So let's try and put everything together. So first thing you observe is, the first observation is, let's check if x and y are independent. Are x and y independent? So the first thing for independence, what you have to check? You have to check if the joint densities multiply out. Right? So what you do is you take f sub x at x and f sub y at y. You multiply the two. So x was again normal 0, 3 by 8. So you have a root 3 by root 4 e to the minus 3x squared by 8 over root 2 pi. So that's this. And then you have the same thing for y. Root 3 by root 4 e to the minus 3y squared by 8 over root 2 pi. You multiply the whole thing out. What do you get? You get 3 over 4 into root 2 pi root 8, 3 over 8 pi. Okay? And e to the minus 3x squared by 8 minus 3y squared by 8. This is what you get to multiply that. Okay? And clearly, if you go back and look at the joint density of x, right? Joint density of x and y as this guy, right? Let me put that in the copy code. Copy it. And bring it down. From here, let me put the copy code right here. So, but joint density of x and y is equal to this. So this is one thing. This is one thing. This is for all x and y. The joint density looks like this. The plot of the margins look like this. So clearly, f sub x at x times f sub y at y is not equal to f at x y. Right? Therefore, they are not independent. So the implies not independent. Not independent. Right? So the first observation is that x and y are not independent. Joint densities don't multiply. That means you'll have a nice conditional density. So that's nice. So let's try and do the what's the conditional density? Conditional density of y given x equal to x. So let's try and compute that. So what's it going to be now? We know that f sub y given x equal to x at the point y is going to be in green. So let's try this also in green. Given x equal to x. So we have x equal to x. So we know that's going to be the same as f at the joint density evaluated at x and y divided by f sub x at the point x, right? So x of x at the point x. So that's the joint density. That's the conditional density of y given x. The joint density divided by the margin density. So what's that going to be again? Let's go up. The joint density is this. The margin density is there above. Is this. So you can just evaluate those. What do you get? You're going to get. I copy that down. That's going to be equal to e to the minus. E to the minus. E to the minus. At the top I have again I have let me erase this a little bit. Equal to root 3 by root 4 4, and I have 1 over root 2 pi, right? Sorry, this is the top is just a joint density, right? Sorry, so it's just going to be just root 3 by 4 pi e to the minus of x squared minus xy plus y squared, the whole thing by 2, and the whole thing divided by f sub x to the point x. So that's going to be equal to root 3 by root 4, 1 over root 2 pi, and I have e to the minus 3x squared by 2. So this makes things consistent. Let me put all the x's in green. That's clear for you. So I have e to the minus x squared, xy, and 3x squared. So then I come down, so x is a constant, so y varies. So y is any element. Here x is just fixed. Right? Then what do I get? I get this is the same as root 3 by root 4, all cancel off. I just get 1 over root 2 pi. Here, and I get e to the minus 1/2. I'll have a y squared at the top. The xy will be there. So I'll write minus xy minus x times y. There. And then I bring this up. So what will I get? If I bring this up, I should get 3 by and an x squared there. So it's minus xy. I'll get a plus x squared by 2. That's exactly right here. So I'll do it again in green. That's the algebra you can do. So the whole thing is going to be equal to now 1 over root 2 pi. Let's see, 1 over root 2 pi e to the minus 1/2. I'll just rewrite this as y minus x by 2 the whole square. It's x by 2 the whole square. And this is true for all y and r. So what I got? I got f sub y given at x equal to x at the point y is going to be equal to this. So now if you stare a little bit again, this looks again like a normal density with mean x by 2 and variance 1. Simple exercise. Therefore, this will imply that y given x equal to x is normal with variance 0, mean 0, so mean x by 2 and variance 1. Mean x by 2 and variance 1. So then now you can see that the mean of y changes if you know what x is. So in some sense, let's just go back to the split view again. Let's check what's going on. Let me go back again and just bring it down. Let me go back up. So here we found out that the individual density of y, or even here a little bit below, is just normal 0 variance 4 by 3. But then you come down here and you find the conditional density of x, y given x equal to x, the mean moves to x by 2 and the variance moves to 1. So for the dependency on x and y is kind of bared out by this idea of conditional and they're not independent. We check first. The next thing we check was the conditional density changes with x. So this is something we will play with maybe on Thursday a little bit more. While I close these ideas, if I get a chance, this x and y they come from a very interesting family of distributions. They're called the so-called bivariate normal distributions, and bivariate normal, which we can discuss. It's kind of on a side. So they both kind of have this normality with them in some dependent way, and the marginals turn out to be normals, but with some dependency. So the y given x is normal with mean x by 2 and variance 1. Excellent. Now, I just want to do some little bit of switch a little topic. So I understood now how x and y behave together, and how to understand independence and individual distributions like margin space. Now I want to do just a little bit more work with random variables in a sort of a, when they're independent, how to understand functions of them. So here's 5.5.1. So two things I would like to do today is one is the distributions of sums of random variables. Of sums of them, of independent. So here the idea is that I have x, I have y. We have two independent variables. Right? And let's assume also that that f sub x be the marginal density of x. F sub y be the marginal density of y. Of y. Let's say I have this. Then I'm given z is equal to x plus 1. Z is equal to x plus 1. Then, so the question is, what is the PDF of that? That's what I want to do. Okay. So here again, the idea is that I have two random variables x and y. I have x plus y, and I want to understand the PDF of that. So now go back to the old calculation we did. Right? If you have a transform random variable, we did in 3 steps. Right? We found the distribution function of the random variable, of the transform random variable. We differentiated it to find the density function of it. Let's do the same way. Step 1. Let's do step 1. Step 1. Let's find the distribution function of that. Right? What's that going to be? That's going to be f of z is equal to the chance that z is less than equal to z. So let me make the z into difference. My handwriting is not hindrance. Z less than equal to z. What's that going to be now? That's going to be the same as the chance that x plus y is less than equal to z. So now I have to find when is x plus y less than equal to z. So that, remember, that's like a simple region, right? Let's say this is the x-axis. Let me put this x-axis right here. Y-axis. Okay. Let's say x-axis here, y-axis is here, and let's say the point z is somewhere here. Okay. Let me make all this in z. So that means you're here, so x plus y less than equal to z, right? So that means, so you just think a little bit. That's just the same as, let's say you can let x go from 0 to z, x goes 0 to z, then y will have to go from, or we let z somewhere here, let's say, z is a positive number, let's say this way. You want, let's say you want x going anywhere here, so this is a line, let's draw the line x plus y equal to z, x plus y equal to z. So that will just y is equal to minus x plus z. So x is 0, y is this, and you come like this. background blue. So y plus x is equal to z. Will be a line like this. So you know, starts up here and then sort of comes down like this. So, and all the points, so this x can go anywhere you want, and y will go from this point to this. So y will go from for any point x, y will go from here till this line. That's how y. That's the region where x plus y is less than or equal to z. That's what. So now, so this is the region. So let me write this down. This is the region x plus y is less than. Right, that's the region. That's how the region looks like. So now you know that this is where capital X and capital Y have to be for x plus y. So now we know, since x and y have joint density, let's say if they had a joint density, then you know that this guy is going to be from minus infinity to z for the y guy, and then inside I have x going from minus to infinity. I'll have f at the point x comma y, dx outside first, and then y no y dx. So that's exactly how you write this density. The problem. Right? This is how it's going. So now the idea is now the fact of the matter is that, or I should say, maybe I should not write like this. Right? Z minus x. Z minus x. Let me use this. This point here would be z. That point here is z. This point here is z. That's okay. This point here would be z minus x. This should be z minus x inside. So let me write down the y outside. So y inside. Sorry. So the y is inside. So the y is inside. So dx. So this x goes from minus to infinity, and it is in black. And the y is inside, so I have dy, and I have y going from minus infinity to z minus x. So you go to z is this, and then z minus x. And that's how the probability will be. Right? This is the probability that, so that's down, this is the probability that f sub z is less than equal to z, is less than equal to z, is given by this. Now if you stare a little bit, the first thing you observe is x and y are independent, right? X and y are independent. So this would imply f at x comma y is just the multiplication of the two density. So that's by independence. So you put that in, so the above is equal to minus infinity to z minus x, z minus x. I have f sub x at the point x, right? And then I'll have an f sub y at the point y, dy. And the whole thing divided times dx. That's what I have. That's just the joint density. So now if you observe a little bit, if you just do a change of variable, just the exercise to try. So I'll do the exercise to try. The variable is just going to be minus infinity to z on the outside, if I leave the z outside, and I call that dummy variable, let's say, as u. So minus infinity to z, I have dummy variable inside of u, and the inside guy, I integrate the x part. I switch the x and the y, so I get inside, I get minus infinity to infinity, and inside, I'll have f sub x at the point x, and I'll have f sub y at the point u minus x. U minus x. Dx. That's just a change of variable idea. Just have to do a simple calculation. So now what do I have? Now I have f sub z at the point z looks like this. Looks like this. So now if I differentiate, so this will imply f sub z at the point z, if I differentiate the above, is f prime of z as z. By fundamental theorem calculus, I just get the integral from -infinity to infinity f sub x at x times f sub y at the point u minus x. I just integrate out u minus x. Sorry, dz, dz. So, the z. Sorry. If I differentiate, I just have to put wherever u is, I have to put a z. Z here, and I have a dx. So that's the density of z. So what we have shown is, we have shown this interesting theorem in the above calculation, which I'll give you in a second. The following idea that the theorem is that x and y are independent variables with PDFs f sub x and f sub y. Then you let z equal to x plus y as a PDF given by f sub z at the point z is the integral from infinity of f sub x at the point x, f sub y at the point z minus x dx. That's an interesting fact we have shown. This calculation. So let me just do a recap. So the idea was that if I had two independent random variables, z, x, and y, and I took the sum of them, then what I would get is I would have to do two steps. I would find the distribution function of z, then I would differentiate to find the density function. That's it, the distribution function, and then step 2. Step 2 is I would differentiate and find the density function of that. So distribution function, when you find, you have to just look at the chances z less than or equal to z. That's the same as x plus y less than or equal to z. But that's just assuming that x and y belong to the region R. The region is the blue region. And that will just give you that f sub z at z is this integral of minus infinity and minus infinity z minus x. But x and y are independent. So that means the joint density is the multiplying of the two marginal densities. And that gives you this expression right here. And then a small change of variable will just give you that, and a flip of integration of x and y will give you this minus infinity z and the integral over x of the entire region of f sub x at x, f sub y at u minus x. Once you have this, the distribution function of z is determined. You differentiate to find the density of z. So these are called, this is sort of you must be aware, if you just tell a little bit, that that one observation is that the PDF of Z, another fancy way of saying it, is what's called the convolution of f sub x and f sub y. So that is some random variables with densities will become convolutions. We have seen this in a discrete case as well.